This lecture starts our discussion of location problems. Location is important to logistics engineering, but the reason we're starting with location beyond just the importance of this topic is that it is a very good way of learning modeling, in particular how it applies to logistics engineering. I think one of the reasons for that is that it's very graphic or physical. You can see the objective function, you can see results. So it's a good way of getting feedback on modeling. Starting with a taxonomy of different types of location problems, the first major division would be between cooperative location problems and competitive location problems. And there's an example in a minute that describes the difference between these two. We're not going to be covering competitive location problems to any great detail, so you can see there's nothing really beyond just an introduction to competitive location problems. We're going to be spending most of our time on cooperative location problems, and then amongst cooperative location problems, the major division is between mini-sum location problems, and then everything else is grouped as nonlinear location. So that implies, which is true, mini-sum location is essentially a linear location problem. It turns out to be relatively easy to solve, but also very appropriate as a way of modeling the types of logistics problems that we'll be looking at. Going further down the hierarchy, the next distinction is between location problems where the primary focus on deciding what's the best location is transport-oriented issues. The cost where you locate has a big impact on transport cost, and transport cost is by far the largest component into producing whatever the logistics network is producing. If that's not the case, then all of that gets grouped into what can be termed local input-oriented location. Most real problems have a mix of transport and other local input related location issues, but we're going to be focusing primarily on the transport oriented where they dominate. Doing local input oriented location includes other things like taxes, labor cost, etc. Again, that's important if you're doing a proper location. In our case, we're going to be looking at primarily just how location impacts transportation in particular. And then for transportation itself, that can be divided into two ways. One is if the location decision is primarily resource oriented, meaning that we're dealing with weight losing activities that we want to locate close to where the source of the resource that goes into the supply chain is located. And then at the other extreme are market oriented location problems where we're trying to locate close to where the market for the product is. And again, you'll see that all problems kind of can be classified roughly using this type of taxonomy. So the first problem we look at is the difference between competitive and cooperative location. And the problem we'll be using is an example that has very specific modeling assumptions, and really nothing about the problem is really arbitrary. Everything is done so that the assumptions we make have plausibility. And the setup is that you have a beach and you have two hot dog stands. One hot dog stand by itself could locate anywhere, and assuming then customers are going to visit the hot dog stand. As soon as a competitor goes to the beach, if they locate right next to the current existing hot dog stand, then assuming customers are indifferent, they'll go to the closest hot dog stand, which would be the green one. So it would get more market share, assuming customers are uniformly distributed. So the net result, assuming that they're hot dog stands and they're easy to pick up and move, is that eventually you'll end up with two hot dog stands located right at the middle of the beach, essentially splitting the market. That's the predicted competitive solution. In terms of our modeling framework, we can model it, we'll call it the competitive beach problem. And here the objective function is that each of the two hot dog stands wants to maximize their share of the market. So they want to pick a location that maximizes that. The constraints, first is that they can pretty much we want to solve for where the stand actually locates, which can be anywhere along the beach. And then in terms of constraints, there actually are no constraints for this particular model. What we return then are the final locations of the hot dog stands. And for this problem, these are the 4 different assumptions. Again, the setup for the problem makes it so that these are all reasonable assumptions. First, 2 stands are owned independently, so each is competing for customers. Second, customers are spread uniformly along the beach. That's why we picked a beach as opposed to other configurations where it would be more likely that customers would cluster. But in a beach, you typically want to locate as far away from other people as possible. So assuming uniform distribution of people is reasonable for a beach, which would not be true for most other environments. We can also assume that they're selling identical products at the same price. This doesn't have to be true, but we're assuming it to make our simple solution actually solvable. And then finally, we assume that the customers buy from the nearest stand. Everybody being a little bit lazy, it's identical product, and they just want to buy from the stand that's closest. So with these assumptions and this model, we end up, in terms of result, to end up with the problem where we have 2 stands located right in the middle of the beach. And for convenience, we've labeled the beach going from 0 to 1. This could be 1 mile long beach, for example, and they end up locating at the halfway point. In contrast, we can also look at a cooperative location problem. And here, imagine the beach, say of that beach or a different beach has been acquired by one company and they want to set up a resort. So for this problem, instead of competing for business, the 2 stands can actually share the customers. Well, the final result would be, in this situation, that the 2 hot dog stands could be located at the 1/4 mark and the 3/4 mark. The difference here in the cooperative problem, where you have one firm deciding where to locate their objective, instead of maximizing the share of market, now what they want to do is minimize the average distance a customer travels to the stand. And why do that? Because they want to serve customers with the least amount of friction. In this case, they're going to solve for, again, where the stands locate. There are no constraints. Returning a pair of stands. So all of this stays the same. So in green shows what is actually different. So it's just the change in the objective function. And then one of the assumptions switches to a single owner controls both stands. With that, we get that solution. So that's a major distinction then between cooperative versus competitive. We can actually then look at how far customers would walk on average. In the competitive scenario, on average, assuming capital X is the distance of the beach, the average customer round trip travels half the length of the beach on average. Again, customers are uniformly distributed. If instead we have cooperation, then we essentially cut by half the average distance that a customer travels. So question then is, why not just cooperate? Why have competitive location? Well, the other thing that's not being considered is that when there's no competition, it's likely that the cost of the hot dogs would be higher. So now we have a trade-off between if we have cooperation, we walk shorter distance, but we have to pay more for the hot dogs, and then vice versa for the case of where we have competition versus cooperative. So question then is, we basically have a problem of customer choice. So assume we have both types of beaches, one a competitive beach environment and the other a cooperative beach environment. One way of modeling this is that customers now have a choice of which beach to go to. So one doesn't necessarily dominate the other as being better, but to be able to create a single model that captures customers' choice of beach, we have to make 2 things commensurate with each other, because both the price of the hot dog and the cost for walking from where the customer is to the stand have to be included in the objective function. So we have the hot dog, which is already measured in dollars, but then the value of having to walk has to be included. So to do that, we're going to include a variable C, as representing the cost for any particular customer of what do they value the cost of having to walk per mile. Essentially, how much would they pay to reduce by 1 mile the distance they have to travel to get to a hot dog stand based on the cost of the hot dog. So with both those factors in the objective function, then we can solve for, in terms of what the output would be, which beach the customer visits, either the competitive or the cooperative. And which beach is then going to depend on how much they value the cost of the hot dog relative to the cost of having to walk. So now we've essentially enriched our objective function to include both of those. There's still no constraints on the problem. The assumptions, though, are important here. Here we can assume the two beaches operate side by side. Customers are spread uniformly, so that's the same. Each customer values a mile of walking at their own rate, so each customer can have their own individual rate. On either beach, customer buys from the nearest stand, and then, importantly, a customer picks a beach before picking a spot on it. If they were assigned a spot, then they could be at the cooperative beach and just happen to be located right next to it, so they'd essentially have no walking cost. So they have to make the decision before they know where they'll be on the beach. So for this problem, we can actually model it, and it turns out that depending on the walking costs, the C relative to the price of the hot dog P2 at the cooperative beach versus the cost at the competitive beach, which is P1, based on these three different values, we can basically formulate this as a decision problem. Depending, customers that value their walking cost high will tend to choose the cooperative beach if their cost exceeds this threshold. So with that, we can predict which of the two beaches a customer would actually decide. The next, so that's basically a way of modeling cooperative versus competitive. The next is the nonlinear versus the mini-sum objective. And remember, the mini-sum objective is the one that is the linear objective function. For this problem, we're going to have another scenario. In this case, it's a situation where we have a couple that's moving to the triangle area. One couple is going to be working or going to school in Durham, so they make one trip per day. That'll be the weight, WI. And the other member of the couple, W, is going to be working and going to school in Raleigh, so they have a weight of 2. And this then represents the number of trips each of the respective person has to make per day. So for this problem, we can start in terms of how should we decide where they should locate and pick an apartment, assuming apartments are available anywhere along US 70 or Glenwood Avenue. So they can pick any point. What point would you predict that they would pick, and then what point should they pick? And they're not necessarily the same thing. Well, we could start with the notion of fairness. Probably the one way of considering it is, what's the fair location? And the way we can model the fair location is that the total distance traveled per day should be the same for both. Well, when we do that, we end up with a solution where they locate at the 2/3 point, essentially 20 miles from Durham. What that does is that equalizes the total distance traveled for each of the two members of the couple. So the fair equitable, for this model, the fair equitable apartment location problem, notice that there's no objective function slot in this modeling formation. The reason is that here we're dealing with a feasibility model. The model is basically trying to find a location that makes the distance the same, so it's looking for the feasibility. So the constraint is equity, returning location of the apartment, and then we have these two assumptions. One way of looking at the equity condition is to state it this way, where we want the net difference to sum up to 0. So basically everybody travels the same total distance. Doing that is specifying the first order condition, that net distance add up to 0. With that desired condition for our solution, we can look at the problem and say that this is the answer we want. And then because of that, we can make it so that we have an objective function. And what we want is what objective function, if we take the derivative, solve for 0, ends up with our first order condition. Well, the one that uniquely does that is squaring the distance. So we can reformulate the same problem as a problem with an objective function, and that objective function is squaring the distance. The reason to do that is so that we end up with the derivative that corresponds to our first order equity or fairness condition. When we do that, we can see that that location at 20 miles corresponds to the weighted centroid location or weighted center of gravity location. When we do that, we can reformulate the model, and now we have a model that actually has an objective function, and this objective function is minimize the total weighted squared distance from the apartment. And then subject to, here we don't have any constraints, so we have a unconstrained minimization problem. Turns out that kind of problem is actually easy to solve, and in this case we can just analytically determine what is the centroid. So basically we have the same problem, but now we have what is a more familiar looking type of objective function, and we can solve it with unconstrained nonlinear optimization. And in this case, for squaring the distance, we can just analytically determine that answer. We can look at a different version of the problem now. Instead of focusing on equity, we could look at efficiency. What is the most efficient apartment problem? Well, in terms of our modeling formulation, we can take everything we did for the previous problem where we were squaring the distance, and if we just get rid of the squaring of the distance, just take the distance by itself, now we have a linear objective function. The squared distance was a nonlinear objective function. So with that difference, everything else about the problem is the same. The location that minimizes that is actually this piecewise linear objective function. This represents the total distance traveled for all the different locations. And as you can see, located in Raleigh is the point that minimizes the total distance. In this case, it's 30 because they're the distance for the one trip from Raleigh to Durham. So that's the efficient solution. So the question then is it do we want an efficient or a equitable solution? Again, there's not necessarily a right or wrong. They're basically just two different models for two different problems. So there's no, necessarily no reason to choose one or the other. The question though is, can we try to get the best of both worlds type situation? And what our next model is a way of trying to include both in a solution. And the way to do that is to look at what are the overall impacts of both location decisions. And in the case of the location being in Raleigh, if it's anywhere outside of Raleigh, the couple needs essentially two cars, one for each to operate each day to travel. But if they locate in Raleigh, assuming their apartment would be located at the school and work locations, they could potentially just have one car for the trip to Durham. So now we have a problem where there's basically a additional factor in our objective function, and now we're going to be looking at the total cost to the couple. So it's basically, and to do this, just like we had to include hot dogs together with the travel cost of the hot dog stand, now these two factors have to be made commensurate with each other so they can be combined in the same objective function. And here they're going to be made commensurate by putting a dollar cost, just like we did with hot dogs and travel to the hot dog stand. So here we're going to include the partner's travel valued at whatever their shared rate is. So we assume the couple values or essentially cost out their travel distance, and that can be then made comparable to the cost of the vehicles that that both of the couples need to be able to reach their jobs and go to school. So now we have a problem where we have an objective function with these two elements made commensurate. We're solving for the location of the apartment, which can be anywhere along the corridor. Here we have now a new element, which is whether or not a second car is kept, and that's a yes or no decision. And the constraint is the one-car solution. The one-car solution is only possible if the apartment is located in Raleigh. As soon as it leaves Raleigh, essentially any X value less than 30, the couple has to have two cars. These are the additional assumptions. Here we're making the assumption that the cost C dollars per mile is how both people value, and we're assuming it's the same. In reality, as you would probably expect the couple to have different values. Here we're going to assume, again, it's a cooperative problem in this case, so they're cooperating and coming up with a single value. We're going to assume that the burdens can be rebalanced by compensating tasks, doing things like cooking. The member of the couple that doesn't have to drive to Durham could spend the savings and time doing things like cooking for the couple. So again, there's a positive for both. And we assume also that the couple coordinates fully. So a single objective speaks for both partners. Most couples, probably this isn't exactly accurate. There's always some friction, but we'll make this an assumption. So this is important. We're actually stating this as an assumption, knowing that the real world probably doesn't quite match up to this. This model 7, we basically have a situation where we can take the model, but to be able to really solve it, we have to be a little bit more specific about it. So we're going to use the next rung of the modeling device. And that particular next rung is where we have a situation where we actually want to create a mathematical description of the problem. So here we explicitly call out the travel cost, the lowercase c. C sub v is the vehicle cost. And now we have two decision variables. X is the location of the apartment, but now we have a new binary decision variable that takes values 0 or 1. It has a value of 1 if a second car is given up. Otherwise, if we have both cars, then it's 0. And the way that works is that by z being 1, it basically forces x to equal 30. And then if z is 0, then x can go anywhere between 0 and 30. So by putting this constraint along with this binary variable, we can have the value of z then decide whether or not we have 1 or 2 cars. And that variable z then goes into this objective function. And then if we give up the second car, then that value of 1 is subtracted from 2. So we only have 1 times the cost of the vehicle. If z is 0, then it's 2 times the cost of the vehicle. So that decision variable now is feeding into our objective function. This way of modeling, we'll be seeing this quite often throughout the semester when we get to mixed integer linear programming, which is essentially the model that we're looking at. Again, we're not going to solve it, but later on when we get to actually using functions to solve these types of problems, we'll be able to actually solve a problem like this. But this just shows the types of modeling that can be done for a problem like this. And then the last part of the lecture talks about how you actually solve these mini-sum problems by hand. Again, we can model it here. This is the actual procedure. And then if you read through the notes, you can see that solving it by hand is essentially adding up all the weights and then solving for finding the median location. And the median location is the point at which the cumulative sum of the weights equals or exceeds half of the total weight. Right. And then there's an example given for I-40 to determine what is the optimal. So again, for one-dimensional location problems, if we have the linear objective function, we can by hand solve to get the optimal. For almost all other problems, two-dimensional problems with great circle distances, None of those will be able to be solved by hand as easily, but there are some special cases that can be solved by hand. What really makes it work is it is actually a linear objective function. And really the takeaway from the entire lecture is that it turns out that this is a really easy way of solving these problems by hand. There are a lot of problems that actually are one-dimensional. We can solve the many-sum location problem by hand for these situations. And in practice, this is actually not a bad assumption to make. We don't have to assume that distances are squared or any type of nonlinear objective function. And the reason is that for most logistics problems, instead of a couple having to share the burden of driving, instead a company hires a transportation company and they pay truck drivers, and they typically get paid per mile. So a truck driver is relatively indifferent for the total miles. They probably would prefer to drive more than less. They'll make more money. So for when you're paying a truck driver, assuming that the costs are proportional to the distance is not an unreasonable assumption. But for a personal problem like with a couple, you basically have to do a lot in terms of modeling to make that realistic. The more common thing would be just to have an equitable solution, which in terms of total distance travel is not as efficient. So there's a fundamental difference between equity and efficiency for most location problems, and it just happens to be the happy case that for most situations where we're actually dealing with companies that pay truck drivers, it happens that the easy approach is also the efficient approach. So it's really a win-win. And that's really the main takeaway from this lecture.